Okay. Well, thank you very much. So, okay, so this talk is about neural networks and this idea of inductive bias and how it relates to this important question of generalization. So to introduce, I mean, the sort of the motivating question, I have this little puzzle. So if there's any Turkish speaker among you, I know there's at least one, so please don't answer the question. And like, suppose I give you this word, daire, and I give you this picture. And I ask you, what does this word mean? What would you answer? So I'll wait until somebody jumps in.
No, blue dot.
Or you can write it on chat. Blue dot will answer. Yeah.
Blue dot and blue circle.
Thank you very much. Blue circle, blue dot, and that's exactly the well. So you could have said also just a circle, or you could have said blue. Yeah. So and that's exactly the point, actually. So there are many possible conclusions you could work from this example. So that's the induction step, kind of, in this inductive bias. You could have concluded that this is a circle. You could have concluded that this is blue. And Vijay, you're the first one who ever said blue circle and blue. I always give this third example. I never had anyone actually picking this. Thank you for doing that, actually. Turkish might have been a sophisticated word with circles and geometry and colors, and we would have a single word for a blue circle, and so on and so forth. There are many examples, right? The correct answer was actually a circle. And I just want to make two obvious points from this. I mean, actually, one definition first. So what is it that makes you choose circle versus blue circle? I mean, it could be your education, it could be evolution, it could be the environment you grew up in, society, I don't know, some linguistic factors that are this and that. So inductive bias is basically all these factors that guide the learner to choose one generalization over another one. So I'm speaking loosely over here. We'll be more precise about this. And then I want to make sort of two obvious points about this. One, generalization relies on inductive bias because, I mean, whenever a learner is making a prediction about, an unseen task, example from a task, that prediction relies on a bias towards a certain solution over other ones. It's always there. You cannot get rid of it. And two, good generalization performance requires certain inductive biases. I mean, the example that this was a circle, not blue, has to do with some bias that's built in us. Okay. So why is this an interesting question? Why is this an interesting question in terms of neural networks? So what I want to show you is that now neural networks have very strong inductive biases. Okay. And to illustrate that, I'll use the simplest example I could think of. So we're going to have this two-layer neural network with 100 neurons in each layer. So that's about 10,000 parameters. Okay. And there's a scalar that's going to go in, and we'll ask it to produce a scalar at the output. So, and these are, I think, tangent neurons, basic hyperbolic tangent activation functions. Okay. And we're going to ask this neural network to basically train on a very simple data set, just 2 points. Okay. So these are the points. This is the input and the desired output, and that's the input and the desired output. And basically make predictions everywhere in between. Right? So this machine is going to do some kind of a function approximation. Now, this is a very nonlinear machine. It has a lot of parameters and it's very expressive. So it could fit, in principle, basically any wiggly, curvy, periodic, non-periodic shape, functional form to these 2 points. But when you throw in all the complexity of sort of deep learning into this, your TensorFlows and Adam optimizers and this and that, and try it for yourself and see, what it ends up doing is basically finding something reasonable and simple. So basically, it ends up fitting more or less aligned to these 2 points. Okay, and there's some kind of, so that is in a sense an inductive bias. The idea, I mean, of fitting 2 points with a simple function is, I mean, the network is biased towards these simple solutions. And there's some kind of an Occam's razor going on, right? The idea that I can explain this data with a simple solution. So the problem statement that I want to address today is that, well, okay, first, that neural networks are strongly biased towards simple solutions. And we want to understand what this strong means and what simple means, right? So to our intuition, I guess, coming from our like years and years of education in mathematics, a line is a simple function, but why is also a simple function to a neural network? Can we understand this? Okay, now this question is relevant. I mean, it's relevant from multiple points of view. One, from the point of view of course, deep learning and machine learning. I mean, many of the current modern models out there are over-parameterized. I mean, so it's just examples from this famous ResNet architecture people used for image classification tasks. I mean, they have parameters on the order of 50-ish millions, and image datasets have parameters, data on the order of 1 million samples. Even more so, this over-parameterization is more apparent in the current language models, which has reached 100 billion-ish parameters, which is huge. So I mean, in this over-parameterized regime, you expect the effect of inductive bias to be much more strong, because I mean, again, these networks are relying a lot on its own internal biases rather than data. So we need to understand that. But it's also important to understand from the point of view of the brain. I'm a neuroscientist, that's why I want to classify myself as, but this talk is mostly going to be about deep networks, but this is the reason I actually came to study this problem. Now, the brain human brain has about 10 to the 11 neurons and 10 to the 14 synapses. And so you can think of these synapses or the connections between neurons as its adjustable parameters and ask, well, is the brain over-parameterized? So Geoffrey Hinton famously made the following observation. Yes, the brain has about 10 to the 14 synapses, and we only live about 10 to the 9 seconds. And so, I mean, if you're thinking of a supervised learning setting, to be able to have enough synapses, parameters as a number of parameters in the brain, so enough data, you need to be getting about 10 to the 5 labeled data per second. So it's obviously not happening. To be fair, I mean, Hinton was arguing for unsupervised learning to be able to fill this gap, because we do get all this unlabeled data, which is streaming to us through our sensory organs, I mean, eyes and ears and that kind of stuff. But if you talk to a neurobiologist, they'll immediately say, well, that's not it either, because I mean, this is a quote from a very recent paper in Nature Communications that was actually making this point, that most animal behavior is not the result of clever algorithms anyway, supervised or unsupervised. I mean, many animals are almost fully functioning from birth, but it's encoded in the genome, okay, the behavior. So this is a common sentiment among neuroscientists that animals are born with highly structured brain connectivity, which enables them to learn very rapidly. To that statement, I'll add basically that connectivity is basically what sets the inductive bias and enables learning rapidly. These ideas are popular to the extent that there was a very recent influential paper that explicitly stated that the brain is a wildly over-parameterized modeling organ. So these questions are relevant from that point of view too. Okay, so with these kind of motivations in mind, so here are the questions that we're going to ask and try to answer in this question, in this talk. So what are the inductive biases of over-parameterized neural networks? What makes a function easy or hard to approximate for a neural network? How many samples do you need? Can we understand this? Can we have actually theory that brings insight to these questions and actually applies to real data? So that's something we're going to show we'll be able to achieve. And the fourth one is more of an aspirational goal. I mean, so can we understand sort of signatures of inductive biases in recordings from the brain? If we could, this would be critical for building naturalistic AI. I mean, I'm not going to say anything about this. This is a research direction that we're trying to build based on some of the things that I'm going to say today. Okay, so these are the questions. So let's see how we're going to address this. All right, so just let's make the first obvious point that neural networks are parameterized functions, right? In goes some vector x, and out goes some vector f of x. For today, I'll make this output just a scalar, but everything I say will have a very sort of easy generalization to vectors. I'll denote by theta the parameters of this neural network. It's the weights and biases and all that kind of stuff. So for each theta, this is a different function, obvious point. And that m be a number of parameters. for this kind of a neural network, and P be the number of training points or examples. So basically, we think of a regime where N is much greater than P. Okay. Now, suppose we took this neural network and like gave it some training examples, P of them, and create the training loss. Okay, maybe a MSE, mean squared error loss, and let this neural network train to 0 error. Okay, and what happens then? Okay, so where's the inductive bias in that? So this is a sort of a schematic picture of how that procedure works. So let this slide be this n-dimensional parameter space, which means every point here is basically an input-output function for this neural network, right? So we start somewhere here. So this is the initial condition, or the initial, this is the function that defines the initial condition of this neural network. And we have n parameters, p data points. If we train this to 0 error, that means we are satisfying basically p nonlinear equations for n parameters. So one might imagine that this leads to an n minus p dimensional solution space. Of course, this is a nonlinear set of equations. You know, there's no guarantee that this is even going to be a continuum like this. But anyway, it's just for cartoonish pictures, let's assume this. So basically, we start from somewhere here, and we're going to end up somewhere on this kind of dimensional, n minus p dimensional, whatever dimension means, a solution space. So what's going to take us from here to there? And that's the learning algorithm, right? So we have this cost function and gradient descent, or whatever other learning algorithm that you have that takes you from here to over there. Well, I mean, and you can imagine or think of this choice as an inductive bias, right? So because I mean, I could have chosen a different learning algorithm that could have taken me to this point, which is a different input-output function. It will have different, while it does satisfy or fit all the data points for training set, it will make different predictions for the test set. Therefore, is going to end up having different generalization performance or that point. Okay. So just by looking into this, right? So, I mean, if you want to understand this this inductive bias generalization and so on and so forth, we need to understand basically the following things. So the properties of this function space, right? What kind of functions a neural network can express? What is the space? I mean, the loss function, okay, and the learning algorithm. I could also add, I don't know, how to initialize this neural network to this list. The network's architecture and that kind of stuff is basically all hidden in this function space. It's basically used, satisfies or constrains the kinds of functions this neural network could produce. So, short answer, well, there is no sort of shortcut to this problem. If you want to understand this problem, you have to address it in full complexity. Okay, so that's one bad news. Well, but what do we do then? I mean, do we just stop here and give up, or do we continue? So this is obviously a hard problem. Well, I'm trained as a theoretical physicist, and one of the things theoretical physicists do when posed with such a hard problem, is to simplify and ask, is there a relevant simplification of the problem which we can get some analytical insight? It will be nice if the simplification is relevant to the problem and also not trivial, so we get some non-trivial insight. Okay. Well, it turns out there is a particular simplification now that is relevant and is amenable to analytical insight. Okay. And that is the limit of infinite width. So we're going to be talking about feed-forward neural network. Okay. And by infinite width, I will mean that I'll be just keep adding more and more neurons to basically each layer until the width of that layer, the number of neurons in that layer, goes to infinity. Okay, and this is relevant because this is sort of an infinitely over parameterized regime, because the number of parameters just goes to infinity. Okay, and we're gonna have just a standard neural network where input goes and passes through sort of nonlinearities and gets weights linearly weighted and passes another nonlinearity layer by layer, and we're gonna do a particular initialization scheme, which is not, which is a pretty standard thing. We'll initialize our standard weights from a Gaussian random variable. So that's what we're going to do. I'm suppressing biases here for simplicity. I mean, they don't pose a problem for what I'm going to say. And the only thing that maybe we need to pay attention here is that I'm going to rescale the total input that goes into next layer by 1 over the square root of the number of neurons in the previous layer. Now, this is actually a very reasonable thing to do because as you're adding more and more neurons, I mean, these are random numbers, their variance also grows with more and more neurons that you add. So if you divide by this, the variance stays order 1 with respect to the width. So you get a meaningful limit, nothing is blowing up or, you know, so on and so forth. So this is a very pretty reasonable kind of normalization to do here. Okay, so we're going to take this limit, and in that limit, some things are going to simplify. So what is going to simplify? So here is some experimental figure from some folks at Google. So, so what they're plotting here is the following thing. On the x-axis is the width, how many neurons I add per layer. And on the y-axis is basically the so-called normalized change in weight. So this is the difference between the this whole parameter vector, okay, just concatenate into a vector, compared to the parameters at initialization. Frobenius norm normalized by the Frobenius norm at initialization. So how much these weights change with respect to where they were at the beginning. And what they found was basically these sort of power law kinds of scalings. These relative changes keep falling with width, you know, and basically making the point that like as you go wider and wider, basically the relative change in the input or the distance with which you need to travel in weight space is basically does not grow. It actually gets smaller in these relative terms. Okay, so another
question, a quick question on your so the connectivity between layers, is that dense or is that?
So yeah, okay. So in this particular setup, it's dense. Everybody is connected to everybody. So everybody is initialized with this this 0 versus 1 thing. Sorry, this.
Yes, I guess that's where the field limit is coming into play. Anyway, go ahead. That's fine. That was more my question from that viewpoint. Yeah. Okay.
If you have a question, I'm sorry, I didn't catch your question.
No, I was just saying the dense connectivity is what gives you the mean field limit, right? So that's
exactly. So I mean, so dense connectivity is there's going to be some kind of central limit theorem that's going to appear. So we didn't get there, but we'll get there, certainly. I mean, usually when people say mean field, they do refer, I mean, technical, they do refer to a different normalization, but I know what you mean. So you don't mean that. Yes, there's going to be some central limit theorem applied here. Okay, cool. So my point, so another, okay, so intuitively what's happening here is basically the following. This network becomes so expressive because it has so many parameters and so such that you don't have to really travel far away in weight space to fit all these data points. You can just, you know, in the vicinity of your initialization, you'll always find something that fits all data points. Actually, this statement was also made into a rigorous sort of statement and proved by some folks out there. Okay, so with that kind of an insight, I mean, we can simplify the problem, and the simplification is going to go like this. So again, what we're going to do is specialize to a particular loss function. So meaning I'll choose a square loss over here. I'm sorry about this extra parentheses. So X and Y muse is my label index. So this is the data index. Okay, so this is what the network produces, and this is what it's supposed to produce. Okay, it comes from some data set. And taking this small change in weight into account, we can sort of basically linearize the neural network in weights. So again, this f of x and theta, this refers to a neural network's output with respect to inputs and some parameters. I can just linearize these around initialization, okay? And people have shown basically that exactly for the reasons that Vijay is pointing to in this infinite width limit, there's some kind of central limit theorem in effect, and you know, and higher moments basically start decreasing by powers of 1 over root n compared to the previous moments and so on and so forth. And using that kind of arguments, you can argue, you can show that this is proved in this paper, that the higher order corrections to this this expansion, Taylor expansion, basically, is subleading compared to the first and the zeroth order, the leading term. Okay, in the sense that in the pure infinite width limit, basically this model becomes just a linear model in terms of weights. I just want to make sure that it's linear in the weights. It's still a nonlinear function of the inputs, but it is the training sort of aspect of it with respect to weights becomes linearized, which is easy, which is nice, which makes our life easier, right? So what we could do then is basically plug this into this cost function and basically do our gradient descent, and you get a linear equation, the linear dynamical system, and then solve that dynamical system to zero training error and get the result. Okay, I'm not going to go through the math of it, but at the end of the day, so if you take this and do gradient flow, okay, so we're doing this in continuous time, not discrete steps, to zero error, basically you end up an optimal solution, optimal set of thetas to this loss, and then you can plug that back into this equation, and you basically get the formula for what the learned network output is. Now, I'm going to go through this in a bit more detail. The first thing I would try to point to you is that this is a function not only evaluated on training points, it's also evaluated at test points. So this actually tells you what this network is going to predict in that limit for any input. So it sounds like a good object to study if you want to understand generalization. Second, I mean, okay, so this y vector is the vector of labels. That's what this is. There's another object that appears here. So this object is derived from the so-called neural tangent kernel. So what it is the following. It is the gradient of the network's output with respect to the its parameters evaluated at the initialization. So it's basically this guy dotted it into itself. You can see where it's coming from. I mean, when you plug this in and square it, that's where it's coming from. It is called neural tangent kernel. It's called neural because it's coming from a neural network, tangent because it has to do with the gradients, kernel because it ends up being a kernel in the sense of a kernel method, which I'm going to describe in a second. Okay, and what appears here is basically the kernel gram matrix or its inverse, which is pairwise evaluated on all data points. And also the kernel again here, where one of these, it's a vector, this one is a vector. One of these kernel inputs are fixed to the data points, and the other ones are basically is the free index, which you can use to evaluate all of this. Okay, good. So in this limit, we have an exact solution. Can we understand this? Cool. All right. So what I'm going to do now is basically describe. Just stop this discussion for 1 second. Describe you another problem. This is a problem of kernel regression, and I'll show you that. I mean, that other problem exactly is equivalent to this solution that I showed you, and then combine the discussions again. So for 2 slides, we're switching to a different problem. We'll come back to neural networks. Okay, so there's this other problem called kernel regression, and you can formulate this many ways, and I'll use maybe a bit technical language here, but it will be important. So the goal of kernel regression is to, again, learn a function from some set to real numbers from a finite number of observations. And this function belongs technically in a so-called reproducing kernel Hilbert space. So if you don't know what this is, I'll be more explicit about this in a slide. With inner product, Hilbert inner product on that space. And the problem is defined like this. We're going to have a bunch of, again, regression points, inputs and outputs. And we want to find the function that minimizes this regression loss subject to some normalization, some regularization, which is given by this kernel, RKH's inner product. But the constraint is basically this function has to be a function within that space. Okay. So so just to maybe give an idea, this is a restriction. I mean, it's a restricted set of functions. For example, not every square integrable function belongs to an RKHS. So it is a strong constraint. Okay, and this turns out to have a unique solution too, exactly. And that unique solution is given by this form. It's pretty much like exactly the NTK, the neural tangent kernel form of a neural network, except that there's basically a different K appearing here. This is the so-called reproducing kernel. It's this object that generates all these functions in this reproducing kernel, Hilbert space. Again, if you don't know what this is, I'll be more explicit about this in a few slides. And this is the gram matrix of that reproducing kernel evaluated in data. This is exactly the same object as before. And lambda is coming from this basically regression parameter over here. So here's what I'm trying to say, okay? So on the left-hand side is this kernel regression solution, problem and solution. And on the left-hand side is the infinite width neural network trained with gradient flow to zero training error on a quadratic loss, which gives you a learned function of this form. And obviously these are sort of the same, okay? Except that here's a regularizer that's not zero, and except that this is a very generic kernel. I mean, this is a particular kernel that you derive from this dot product. Okay, so basically what we're going to do is the following. Okay, so up until now I just gave you background. From now I'll actually tell you what we have done. So we're going to try to understand this problem. And we have our techniques are going to come from physics, some statistical mechanics. I'm not going into the detail of this. So, and we're going to have a theory of generalization that predicts, how well a kernel regression performs on test data, given any kernel, any distribution over which you sample your data, and any target function, the function that generates x from, so y from x. So it will be very general sort of theory over here. So this will have its own applications to kernel regression and so on and so forth. And then we can take the limit that lambda goes to 0 and replace this k by KNTK and get basically insights about how neural networks work. And this will allow us to address this inductive bias question and simplicity bias and all that kind of stuff. Okay.
Cengiz, a quick question on this. For the neural tangent kernel, you only know it for a few networks, right? Either one layer networks or two layer networks. It's not known in general for arbitrary, right? Or
there are formulas for it, so you can define. I mean, I guess depends on what you mean by known. So if you're saying that, like, if it exists, if you can express there's a set of special functions of x and x prime, you're right. But I mean, for generic, let's say value networks of infinite, so deep, there are formulas which you can define as iteratively from one layer to two layers and so on.
Okay.
Okay, but when we use this applied to NTK, I'll comment on. Yeah, you will have to at some point do some numerics. I'll comment on that. Yeah, there are cases where we can address this sort of analytically, and there will be some cases where we'll have to calculate this NTK or its properties numerically. Thank you for the question. Okay, so just to state what exact problem we solved. So this is what we solved. So we're going to sample P examples. So this is the data set of that P examples. So the inputs X's are going to be sampled from a particular distribution. I mean, this distribution can be generic. We don't have to commit to it at this stage. And the Y's are going to be generated by passing these X's through some target function. And this is again a generic function. We don't have to commit to anything at this stage. And adding some noise to it. This noise is going to come from some Gaussian noise. You can set that to 0 if you want. So this is very generic. And then what we're going to do is we're going to take this data set and find the optimal kernel regression solution with some kernel RKHS, and take that optimal kernel solution, optimal RKHS solution, and plug it here to calculate a generalization error. So this is the error between the true target and the optimal solution over here, this time averaged over all possible X's, not just the training set, okay? So that's why I call it the generalization error, because I'm not just looking at the subset of the train data, but the full distribution. And then I'm going to average this over all possible data sets of size P. So maybe like, I don't know, so if P is 10 and this was MNIST, let's say, I'll do this for like choosing 10 digits and then another 10 digits and another 10 digits and another 10 digits randomly digits, and calculating this generalization error over all possible draws of 10. Okay. So it turns out you can, so this de-averaging makes it not easy, but sort of amenable to calculate using statistical mechanics. So you can do this calculation using the replica method. So it's a technical method. I'm not going to even mention or describe how this is done, but you can do it, okay? And you will end up getting a formula for EG, which I'll display in a second. Okay, so I hope what I mean by this EG generalization here is clear. Okay, now, the problem I've described is very general, right? I didn't commit to any P or Y or F or, I don't know, kernel. Okay, so of course, I mean, okay. So that means I have to, I mean, okay, so how is that possible? Okay, so to be able to introduce my result, I have to sort of introduce one more fact, and this is the following fact. So any kernel induces a basis in the space of square integrable functions. Square integrable with respect to this particle distribution. And that sort of basis goes through this kind of an eigenfunction equation. So what goes in here is basically the data distribution. So this kernel object, it has two sort of variables, x prime. So x is the one that's sort of multiplied or integrated for over this eigenfunction. And on the other side is the eigenfunction appearing again. And this eta k is the eigenvalue. So this is the Mercer decomposition. Okay, just to so to this phi k's turned out to be a basis for square integrable functions, and an RKHS, the reproducing kernel Hilbert space, basically corresponds to a subset of all these functions, g of x, which you can express as a sum of these eigenfunctions such that their Hilbert norm, which turns out to be defined this way. These coefficients normalized by eta k is basically less than infinity. Okay, so I'll give examples of this in a second. All right, so why am I pointing to this? Because in a way, this answers the following question: what function space we're talking about? So we can think of the input-output map of this neural network now totally as expressible in this function space in the eigenbasis of this RKHS. Basically with some functions weighted by some weights. Now these weights by no means correspond to particular weights in this neural network. They're complicated functions of them. Okay, we don't even know how to express them. But I mean, this function can be expressed, and this function does belong into this sort of RKHS. Also, the target function, which is also a generic function, a square integrable function, has an expansion in this basis, and it has its own weights. So in a sense, in this particular limit, the full neural network training business can be reduced to a linear model, linear in weights, of finding, getting data, passing them through some nonlinear functions and solving a regression problem there, linear regression problem there, trying to match these W bars. These are the target sort of target weights with these weights from the expansion of the neural network in this basis. Okay, so there's some technicalities here which we don't need to discuss. Just to make the same point again. So there's 2 points of view. One is just take this input, pass it through this whole neural network, and so on and so forth. And the other point of view, just take this input. So in this top view, every parameter weight here is adjustable. In the second point of view, we take this x and pass it through these nonlinearities. This first map is fixed, and these phi's are eigenfunctions. A property of them are they're also orthogonal under this probability distribution P of x. And then basically constructing these orthogonal functions, using these orthogonal functions, we can construct the network's output by just linear summation of them. Okay, so just to tell you where I'm going with this, it turns out there's an ordering of these functions, meaning that this guy has the highest eigenvalue and this guy has the lowest eigenvalue. And this is an easy function for this neural network to learn, and it will turn out, and this is a very hard function for this neural network to learn. So that's what's going to be happening. And you can take any target function and expand this in the spaces. If that target function has a lot of weight here, it's easy to learn for this neural network. If that target function is a lot of weight there, it will be very hard to learn for this neural network. But we'll get there. Okay, so I just need to show you what it is that we get out of this. So you do this calculation and you get a formula. So the formula is complicated, but I just want to point what it involves. So this is the generalization error. It's kappas and gammas. You don't have to worry. These are just some self-consistency conditions that needs to be satisfied. So you need to solve for them. P is the number of samples that you're seeing. Technically, these equations work because it's statistical mechanics in the limit P goes to infinity. However, I'll show you that they work for like P on the order of 10, 20 in practice by simulations. This is generic in the sense that, I mean, so what you need to apply to this to any kernel is basically calculate this, this spectrum eigenvalues and plug them in here. These are the eigenvalues. And these W bars are the target weights. So that's basic. And the sigma is the noise parameter. So you have to be able to apply this theory, you have to take the kernel, diagonalize it, and also decompose your targets in that basis. Sometimes we're able to do this analytically, sometimes not. But nevertheless, I mean, these equations show very rich phenomenology and explain a lot of things about how neural networks work. So I'll just mention a few. Okay.
I guess a few more questions actually on this. Sure. I mean, two. One is the association with the neural tangent kernel. So that also depends on the initial condition, right? So the neural tangent is a function of theta 0.
It is.
And so you'll have different different kernel functions if you have different initial points.
It is a very good point. And exactly, again, for the mean field point you made, in the infinite width limit, there is some kind of concentration happening. So the variance with respect to variations in the changes in the initial condition just disappears. So this actually becomes a deterministic kernel in that limit. Now, of course, if you, in practice, we'll be dealing with finite neural networks, and there will be a variance due to that in this theory, I mean, in the simulations. And I'll show you in simulations exactly how much that variance is. So I'm not going to address that theoretically, but I'll show you in simulations how much that variance is.
So the other question, which was not entirely clear to me, maybe I missed a few things, was, are you studying the annealed system, or are you studying the quench system in some sense?
In statistical mechanics terminology, I'm studying the quench system. The full
okay.
Quench system. Yeah.
So that's the harder thing to study, but I guess but for this, even with the Gaussian setup, there isn't a.
So actually, there's nothing Gaussian here. I mean,
yeah, okay.
Yeah.
I mean, there is no equivalent. I mean, sometimes if you have underlying Gaussian thing, you can.
Sure.
A GUE or something, you can show. Show that the quench system is actually. I mean, it's the same as the annealed thing, and so there's some nice things there. But I guess it's not.
Yeah, so I wouldn't think it would be true for this system. This is, I mean, we addressed the full, that's why we use the replica method. And
okay, all right, no, thank you.
And you know all these things, so, okay, good. Okay, what I want to show you first is that this actually works. So I'll apply it to some real data sets. And then if I can convince you at that point, then I will use these equations to make some inferences about inductive bias. Okay, so let's say, can I use this idea to predict test error in MNIST CFAR10, some data set? Okay, so here's what we're going to do. So the way I wrote this basically was on this sort of continuum kind of a setting. But if you have a finite data set, you can also define a sort of a Dirac measure on that data set. So suppose I have MNIST has 60,000 data points, including train test. I can define a delta function measure, sort of a probability mass on each of these points, and plug this back over here. And what that ends up giving me is basically a kernel PCA problem. This K becomes a matrix that I need to diagonalize, and these eigenfunctions becomes eigenvectors. They're finite dimensional in the sense that each dimension corresponds to a data point. And these eigenfunctions take values on those data points, and then the eigenvalues. Okay, so I mean, I have to solve this numerically. Okay, it's fine. So to apply the theory, we need two ingredients: eigenvalues. I read them from here, and also kernel eigenbases to get the target weights. So how do we do that? So for example, suppose we want to learn this function. X goes from this image to a label represented in this one hot format. You can take these, eigen vectors and just project them onto these y functions and read these w bar k's. Okay, so get your, so the etas, which became a lambda here, I'm sorry, etas from here and wk's from there, plug into the equations and plot your theory curves. Okay, so here's how this looks like. So on the left, I'm showing a kernel regression example. So this is a Gaussian kernel. It's not coming from a neural network, just to show that this works. The solid lines are the theory. The circles are the kernel regression solutions, meaning we sample some data set, fit the kernel, do the test, and average this over multiple generalizations of the data sets. So this error bars over here basically correspond to that, what you asked Vijay, that variation due to, actually this corresponds to the variation due to data sets. So there's no initialization here. And as P was the number of samples, as goes large, that variation drops obviously. And when P is small, on the order of 10, the variation is large, but still the mean is pretty well explained by this theory. On the right-hand side is actually a neural network experiment. So this is a 3-layer NLP, MLP, multi-layer perceptron, trained on MNIST. So with this N is the width parameter over here, that number of parameters, 800 neurons in each layer. So it's not infinite wide, it's a modest width neural network. So this is the theory. The triangles are the kernel regression experiment. So this is done at the infinite width. And the circles are done at finite width. So we trained, let's say, like 1,000 digits on this neural network, 1,000 digits, and then calculate the test performance or generalization performance, and that's what we're plotting over here. Now, these error bars also include variations due to initialization, and also data set. So, I mean, what I see here is a pretty good match. And I just want to point that, a lot of machine learning theories about worst case bounds, and a lot of the times they become sort of, bounds become so much vacuous in the sense that they're not practical. This theory, although does show some deviations, does get the curve on top of experiments. So it's pretty sort of good at this to me. All right, good. So, we have tons of other tests in our papers. Just showing examples over here, and I'll show you more. I hope this convinces you that this works. Now, can I look at these equations to say something about this inductive bias and simplicity, which was my original motivation? Okay, and that is going to come through this idea of spectral bias, and that goes as follows. Okay, all right. So it's a very simple fact that we can take this generalization error and decompose error into each spectral mode itself, meaning this is because we're dealing with quadratic losses. Each mode, because they're orthogonal to each other, has their errors also decouple like this. So I'm going to define this EK to be the difference between the network's learned weights in the sense of these weights of functions. So this is a function of number of parameters, so number of data points, compared to the true weights and normalized. Okay, so what you can prove from these equations is the following: if an eigenvalue, if in a mode, in a particular eigenfunction, let's say space mode, the corresponding eigenvalue is higher, then the corresponding relative error in that mode for any size of the data set is lower. Meaning, these are relative errors. So this neural network starts learning basically the first modes first, and then so it starts decreasing errors in the other eigenfunctions. So there's a preference towards trying to explain data with those guys, and then those guys. Okay, so you can use this insight to define a metric of which I call task model alignment. So this is basically a vector measure of how good neural network aligns with the task that it needs to solve, which is basically a cumulative sum of all the weights up until the kth mode, normalized by the total sum of the weights. So these are all target weights. So if the CK rises very rapidly, meaning the target function is a lot of projection to these top guys, then this is a function that neural network is going to learn fast and good. Otherwise, it will not be. And you can again prove that if a function, if CK is rising very rapidly for a function compared to another function, that first function is going to be learned much faster. Let me show you this in an example. So I'm going to do the following experiment. So which one is harder? Meaning, I'm going to ask a neural network to learn this task of telling zeros from ones versus 8s from 9s. So which one is going to be a harder problem for this neural network? Any ideas?
8 from 9.
Yeah, so I mean, 8 from 9s, that's certainly true for our visual system because I mean, 8s and 9s, thank you, Jeffrey. 8s and 9s have maybe more similar features than zeros and ones. So you might imagine that you need more samples to solve this. Okay, but this turns out to be true. So this is actually, it's a simulation. So the generalization error falls faster for 0, 1, and then 8s and 9s. But why? I mean, this is certainly true for our visual system, but why is it true for a neural network which sees a vectorized form of these zeros and ones? Okay. Well, you can plot, I mean, what our theory told us to plot. So what I'm plotting here is basically the top 2 eigenfunctions and the values they take on this data set versus that data set. So each point here is 1 digit. And on the x-axis is basically the first eigenfunction. And the second, the y-axis is the second eigenfunction. And these are colored into different zeros versus ones. Okay, so what you're seeing is basically in the top, but just by looking at these 2 top eigenfunctions, you can already separate zeros and ones, but not 8s and 9s. So if there's a preference towards learning these top eigenfunctions, it does make sense that these networks learn zeros versus ones first, but not 8s and 9s. Right? So that's what this theory is saying. We can also, I mean, look at basically this cumulative sum, this metric. Basically, again, this was measuring how much. So this was supposed to be k. I'm sorry, how much power is in the up until the kth eigenmode. For this function, again, you see a very sharp raise, and so basically a lot of the power that you need to solve this task is already in the first few eigenfunctions. But this guy requires a bit more, so therefore it makes sense that you learn this guy faster than the other one. Okay, so I'll finish maybe in a few with a few slides. So this was a case where we had to resort to some numerics. There's also cases where we can do even more analytics. So here's a case where we can actually generate an artificial data set to break basically learning in a neural network just by making the target function not align to the top eigenfunctions. And so basically the theory goes like this. If, for example, you had this special setup that you are sampling your x points uniformly over a sample, so uniformly over a sphere in some d-dimensional space, okay? It turns out the eigenfunctions of the NTK are spherical harmonics. So that's a fact that you can show. Okay. And in the limit that this number of dimensions go to infinity, basically what you can show is basic. Okay, well, let's take it. Okay, so spherical harmonics. Let me take it from there. Good. So then you can think of target functions which are formed of combinations of these spherical harmonics. So this is sort of a picture of this. Spherical harmonics have 2 indices, k and m. I believe this is degree, this is order. I always mix these things up. But anyway, so the idea is the following. So this is spherical harmonics on basically a two-dimensional sphere over here that we're looking at. But of course, we're going to be talking about higher dimensional ones. It's just for visualization. You can think of this k index basically a measure of complexity or frequency and that kind of thing. The color here basically is showing the value that ykm takes on the sphere. Okay, so we're going to keep forming more and more complicated functions of this sort. So these functions are going to have some fixed k, meaning they'll have only a certain frequency content or k content, but can have any m content. Okay, so we can show that you need about, in d dimensions, when d is high, about d to the k samples, k being this frequency index, to be able to learn a function that is a pure k, that has only pure k content. So this is what's being shown here. So these different curves correspond to different functions with different complexities. So you need about, this is a neural network, this is a kernel regression, sorry, with 15 dimensions. After about seeing 15 samples, the generalization area curve starts falling for a target function that's only made up of k equal to 1 spherical harmonics. But I mean, so this one shows 15 squared. This is the 15 squared line, and then you start seeing the k equal 2 modes fall. This black guy over here has only k equals 7 content, so it's a very high frequency function. And basically, even after seeing 10,000 samples, there's no learning or generalization basically in that mode, because you would need at least 15 to the 7 samples to even start learning that mode. Actually, if you look closely, this is negative learning in the sense that there's a slight increase in generalization. Here, even like adding more data points is not helping. And again, the solid lines are our theory. So this is a very concrete example where basically neural networks cannot generalize because their inductive bias or spectral bias is totally disaligned with the target that they need to learn. And these are the same things repeated in neural network experiments. So this is a very wide one, 10,000. And this is a sort of a shallow, like a not so wide one with 500. And basically, the reason I'm showing this is basically also show the limits of the theory. If you go very wide, the circles are neural network experiments. They match theory and kernel experiments. If you go 500, you still get the trend, which I think is very good. But I mean, you do also start seeing some deviations. And so one might want to refine the theory to capture them or just be content with whatever is here. So yeah, okay, cool. Let me not even go into this. I mean, there's this other thing called double descent, the fact that like sometimes generalization error can show these behavior that's not monotonic. And we have phase diagrams that explain when these things appear as a function of noise and spectra and that kind of stuff. So let me summarize. So what I just shown you today was the fact that neural networks are biased towards simple functions. And in this particular limit that we worked in, simple means composed of the high eigenvalue eigenfunctions of your intention kernel. This might be a satisfactory or unsatisfactory answer, depending on your taste. Inductive bias is a function of network architecture based on learning rules. For a wide neural network, all these are factored into the spectrum of the neural tangent kernel. 3, this theory actually works remarkably very well for real data sets. And this has implications for asymptotic power law decays observed in many models and learning curves. I didn't have time to explain this. I'm sorry, this was reference to from a previous talk, so this doesn't apply to today. And everything I described today appeared in basically 2 papers, one from ICML last year and one from one this year. But this is not the full story. We've been working a lot on this. We have a bunch of papers coming on NeurIPS this year that basically takes this to an out of general distribution setting, meaning training and test samples are different. So that seems to have interesting examples. Also getting into the idea of a probabilistic sort of domain of probability and taking some of these ideas to Bayesian neural networks. And so this latest one is an archive paper. So I talked about the correspondence between neural networks and kernel machines in the infinite width limit. But it turns out even for finite neural networks, you can make another correspondence between neural networks and kernel machines. It's not the NTK initialization, but it's the NTK at the end after training and the network has converged. So this basically, last paper over here is addressing that and setting up that correspondence and showing that there's another match between them. for finite neural networks. And finally, this is for those interested into neuroscience. So this is a preprint where we took this idea and started applying it to neural population codes, trying to figure out like if there was just a neuron looking at a population of other neurons and trying to learn something from it. Can we ask the question of what is it about the stimulus environment that's easy to learn and that's hard to learn? There are some data sets that are out there which allows us to sort of address these questions. With that, I want to thank my sort of group members and collaborators and funding sources and all that. And then thank you all, of course, for listening and being here with me. Thanks again. And I'm happy to take questions in the remaining, whatever, 3 minutes.
Thanks, Cengiz. So there's a question in the chat. Do you want me to read or can you see the chat?
Oh yeah, I can see it. Certainly. What are these eigenfunctions? You said they're not data dependent, but are nonlinear, but can you say more? Yeah, sure. I mean, I actually show 2 examples of this. So for example, here's another solved case where you can analytically solve them. If the data is uniform sampled over a sphere, these eigenfunctions are spherical harmonics. If not, you have to numerically solve for them. And this is exactly what this plot was showing. So in the case of MNIST, so I don't know a better way of visualizing these eigenfunctions, but this is one way of visualizing them. This is what these functions take. They're not dependent on data, but they take value on data in that sense. Yeah, this is how you can visualize them. I'm not sure if this helps, but I'm happy to add more.
So Cengiz, I have a few questions,
sure.
more long.
But I do see some people raise their hands first.
Oh, sorry.
I'm sorry.
Yeah, please, they should go ahead.
Chris, please go ahead.
Yeah. Hello, thank you. So it's known that neural networks generally find solutions that generalize better when using larger learning rates or smaller batch sizes. Do you know if there's any connection between that and which of these modes the train are being focused on in the inductive bias?
Yeah, so first larger learning, I mean, so both of larger learning rates and small batch size, so both of these are outside this theory. So I don't have an answer, so I cannot address them through here. Yeah, so I'll just leave it at that. We do have a paper looking at basically gradient, I mean, the dynamics of gradient design with discrete steps and then mini batches and so on and so forth. And there, I mean, it becomes complicated. We actually find the optimal batch size for many random feature like models, and that optimal batch size is about 4 and so on and so forth. So, but the story is not this clean. So the equations that come are not very interpretable, but yes, you're right, there's an optimal batch size. And that paper is called Learning Curves of SGD. I'm happy to, if you drop me an email, I can send you the link.
Thank you.
Sure.
Super nice talk, very interesting. So the quantity, this E sub G that you focus on has a regression flavor, right? It's a squared difference. So the first examples you showed were for MNIST, where it's really classification problem. Is this, this might be a really elementary question, but is there a way to sort of understand classification errors from the values of E sub G that you end up with?
Yeah, so I mean, it's a classification problem, which I turned into sort of a regression problem by trying to regress into these vectors. And the reason, I mean, I did this is because all of this theory works with MSE, which makes my life easier because, yeah. So the problem is harder for, you know, a softmax layer, for example, at the end, and which is going to make this into a different kind of problem. However, so this link to kernel regression does not work for different loss function. However, this linearization of the dynamics, meaning that the weights don't change much, actually still applies. So let me go back to that paper over here. So why neural networks of any depth evolves as linear models of gradient descent? So the result of this paper was general in the sense that like that linearization happens regardless of whatever cost function you're looking at. But then of course, if that cost function is something more complicated than this, then the gradient, even the gradient flow dynamics itself is hard to solve. So it becomes complicated.
So in the graph, part of the reason I ask is in the graph where you first showed the plot of E sub G as a function of the, I think the training sample size for the MNIST, I'm not calibrated whether E sub G of 10 to the minus 1 is a good or not so good, I guess, square difference between a one hot vector. I don't know, can you look at that, or can one look at that and kind of get a sense?
Yeah, so 0.1 will be, yeah, so exactly, it's a square difference between a one hot vector and the network prediction. So 0.1 shouldn't be that, because I mean, the norm is basically 1.
Yeah, right.
Exactly. So these are normalized to 1 in a sense.
Right. Okay.
So it's not bad. It's not bad at all, actually.
Yeah. Okay. All right.
But the point, I mean, okay, maybe the point you're trying to make is, are you addressing this in a regime of a neural network where it works well?
Right. Yes, that's what I'm curious about.
That's a good point. I should be more careful about this. Yeah.
And the scales of these two graphs are so dramatically different. Like clearly the left one covers ranges of interest, but I was less sure about the right one.
Yeah. I mean, you're right. But by looking at just 0.1, I would guess that it's reasonably active.
Okay. Thank you.
Thank you. Very good question. Thanks. Jeffrey, you had a question or not?
Oh no, I did have a question, but it was more so I mean, I guess you're looking at so it's, if there are other loss functions, it's not clear that gradient descent is the way to go about it, right? So I mean, maybe you wanted to solve the, if your loss function was not quadratic.
Oh yeah, true. Okay, go ahead.
Yeah, so what type of theory, even if it's linearizable, it's not clear gradient descent is the way to solve it. So in some sense, in the theory that's built up, you need both these things to work, right? In some ways. So
I mean, so that's exactly why I was very careful about the statement about what problem I'm solving here. I'm addressing this only at this particular limit, infinite with neural network training with gradient flow to zero training on a quadratic loss. So all of these have to come together to be able to do this match. Now,
so the question more was like, what happens if that is not the case, and if you have
true. I mean, it is an open problem. But if you look at, I mean, a lot of work in this literature, I mean, they all do rely on these kinds of simplifications.
Well, there are cases where people try mirror descent and other things and different loss functions, and so it's not, and for different problems, different things may happen. I mean, of course, you have to throw the whole theory of RKHS out of the bag in that case, because you don't have the L2 theory doesn't apply.
Okay.
But anyway, so that's
no. You are true that this theory is not going to apply. I mean, if you change any of this, right? I mean, yeah, certainly there's going to be modifications to what I say. That is a fact. Yes.
Yeah. I think there's a question on chat now. So.
Question of?
In the chat.
Chat. Okay.
Chat, yeah.
Question chat. How expensive are the computations in predicting the test error versus just training the network and getting the test error? So this is a very good question. Actually, I mean, the diagonalization, so you can, so the main problem that you need to solve is basically this diagonalization problem. So there are efficient algorithms for doing this. Now, if you're doing this, of course, for just a shallow network and, just a simple network for a small data set or something, there might be cases where, there are certain cases where training a neural network is easier. So my point here is not that this is computationally efficient, even though in some cases it can be efficient. It's more that, I mean, it does give you a analytical formula which you can use to get insight, which was not possible by just, trying error of training neural networks. And also, I mean, there's a lot of quadrature tricks we had to do for example, doing these kinds of integrals and high dimensional spaces and that kind of stuff. So there's a lot of computational cost that goes into getting these theory curves.
Any other questions?
Okay.
Thanks again. Actually, I have more of a comment than a question,
Please.
but like this, I am now curious. I asked you a little bit about this, like learning dynamical systems, and in learning dynamical systems, it's like eigenstructures and identifiability, they come up quite a bit in Hankel matrices. I am curious if there's a relation there, but it's not as clear to me how to pose that question. But I will probably think more, and I will ping you later.
No, we should certainly talk. I mean, yeah, it's. I'm sure there's a relation. we should talk.
Okay, thanks, Cengiz, again for the nice talk. And I think if anyone has any further questions, feel free to shoot him an email.
Yeah, please.
I guess.
I'll be delighted. Thank you. Thank you very much.
Thank you. So, Cengiz, you'll have to end the meeting because you. Right. So then
I'm ending right now. Thank you.
All right. Yeah.